Started. Settle in. Okay, so it's my great pleasure to introduce Alex Smola. I've worked with Alex for about 9 years now, and he's a world-renowned authority on kernel methods, graphical models, and more recently he has been working on graphical models for internet scale problems. He has a lot of exciting things to talk about, things that I'm personally excited about, and things that I hope you also will be excited about. Instead of sort of doing a traditional style bio where I sort of read out the laundry list of things that people have done, I think I'll let Alex do all the speaking this time, and we'll hear from him about graphical models for the internet.
Okay, so thanks very much for the kind words in the introduction. Second remark, I see a lot of purple t-shirts here. Yay, that's great, a lot of Yahoo t-shirts. Did you wear them just for today, for that reason, or? Well, it's a coincidence. Anyway, okay. Yeah, so this is probably a bit different, a talk from some of the other talks you might have seen me give at some of the previous summer schools. And most likely no equations will be harmed today, but it'll get more technical as we go along. So the no equations will be harmed today doesn't mean you won't learn anything. At least I hope you still learn something from it. The point is, I want to give you a little bit of a background of the context in which some of these algorithms run before delving into the details of why we pick specific algorithms for specific problems. And so this is essentially why I think it's quite useful, because not everybody here in the room would have had the chance of working at a big internet company as an intern or in their day job. So I imagine it might be actually quite useful to see a little bit the context in which some of these algorithms run. A lot of it is common sense, and there are like wonderful other slide decks that you can go through. For instance, if you go to Jeff Dean's homepage, he has a really wonderful systems talk of about 50 minutes or so. If you're more interested in these things, I very strongly recommend that you read up on this. It's really nice stuff. Okay, so, okay, there's a range to it. So I said I'll be talking about systems first, and then I'll talk a little bit about applications as to what can you actually use those algorithms for, because one thing that I've actually found a lot in the research community is that people go and solve problems they think are relevant problems. And some of them are relevant problems, and occasionally they are not quite so relevant. And what industry is a really good source for is questions. Not always answers, but it's a really good source for questions. Okay, after doing this, we'll do basic probabilistic modeling. So I don't know how much of that you might have seen already during the summer school, but just setting the scene, exponential families, and so on. Dealing with probabilities. I'll give you an example of a very simple algorithm, namely naive Bayes, and well, then we're going to get more to the fun parts. We'll talk about directed graphical models, a little bit, what they look like, and then further on, okay. The second part of that is going to be quite a bit more technical. So namely then scalable topic models, how to really get the inference settings set up properly. The code for that is by now actually available on GitHub, and it's the fastest LDA code you can currently find by quite a large margin. And I'll be talking more about further applications of latent variable models, how you can describe and explain specific aspects to it. And in the end, we'll talk about undirected graphical models. Whether we'll get much to applications of undirected graphical models in the internet context is not quite clear yet. So far, the slides are tracking at about 320 slides. We have 8 hours. If I run out of slides, there'll be some more. But I actually suspect that we'll get stuck somewhere here, and that'll be about the end of the 8 hours. As in, I could go on talk about this for many more hours than what I have, but there are a lot more interesting talks here. So, given that this talk is for you guys, right? This is not for me, because I supposedly know this stuff, right? You need to ask the questions. So, if something's not clear, raise your hand. Ask a question, right? An ideal thing would be that each of you would have asked me at least one question between now and the end of the class. Probably not all during the class. Sometimes you might be embarrassed and think, okay, is this really an intelligent question? You can ask me after the talk too. Furthermore, if you think something is going too slowly, start yawning loudly, right? That way I know how to speed up. On the other hand, if I'm going too fast and you don't slow me down by asking me questions, I'll just go through it like a steam engine, and you'll be lost. And sure, there will be lots of places we can catch up, but you won't get the optimal benefit of the entire talk out of it. So ask if you have a question. Yawn if it's too slow. Okay, good. And if there's something specific where you want me to talk more about it, no problem, I can do that. And there's a pack of paper and a pen, and I can go into specific derivations for more detail. Sometimes that's more fun rather than looking at the slides. Okay, good. So with that out of the way, let's do something like that I would call systems for dummies, and it's really, really, really just scratching the very bare surface of it. So let's first look at actually the hardware that we're using to run our algorithms on. And I'm not telling you any really amazingly new things here. I mean, this is stuff that you should know, right? So, if you look at the CPU, for instance, I mean, you have 8 to 16 cores, and that number keeps on going up every 2 or 3 years by a factor of 2. You might have 2, 4, 8 chips in one motherboard, so you might have a 64 core machine that you can have. And for different applications, we use slightly different types of hardware. Clock frequency has pretty much stayed the same. It's about 2 to 3 gigahertz. We don't necessarily actually buy the fastest chips, simply because they use up a lot of electricity, a lot of energy. And the trade-off is not necessarily to have the fastest CPUs, but to have the fastest overall system. So you might have something between 8 and 16 megabytes of cache per chip. And what you also have is you have a subset of instructions that are really fast, and they are usually related to multimedia and so on. But it also means that anything doing linear algebra is really fast. And unless you cannot possibly avoid it, you should never, ever code up a matrix multiplication yourself. Always call an optimized one, like, for instance, in Atlas. For instance, Atlas is something that's really good, or the Accelerate framework. But basically, never, ever implement matrix multiplication yourself, or even an inner product between two vectors, unless you have a good idea for it. The reason why I'm repeating is because I've seen it so many times happen. And you lose a factor of 10 to 100. Memory, 8 to 128 gigabytes. Often you have like 2 to 3 memory banks that you slot into it. An important thing is, so the memory chips themselves right now are what's called DDR3. Well, the specifics don't really matter very much, but what matters a lot is that sequential access in memory is easily 10 times faster than random access. You can easily find out about that, for instance, if you do a matrix vector multiplication. We execute matrix vector multiply, and you also execute matrix transposed vector multiply, right? If the code doesn't actually transpose the matrix, this should be the same speed, right? I mean, our CPU hasn't gotten any slower. However, if you actually look at the time, it can be a lot slower. The reason why it can be a lot slower is because the CPU doesn't actually read in, one floating point number at a time. It reads them in bulk. Now, if it reads them in bulk and then you just jump ahead to the next random location, you keep on doing this, well, you're going to incur cache misses all the way through. And that slows down your code a lot. And interesting things like that can, for instance, mean that your code might actually run faster on a laptop than on our highest end server. It's actually happened to us once. Not a joke. This was like a 4-year-old laptop versus a 2-year-old server. So, and you know, there was nothing wrong with the server. It was just that we were using the memory interface wrongly. Hard disks, well, 2-3 terabytes. You can buy them for about $100. The data throughput from the hard disks hasn't really gone up very much. So it's about 100 megabytes a second. I mean, the specifics may be off by a factor of 2 or 3. But the reason why it hasn't actually gone up a lot is because the rotation speed of the hard drives hasn't increased much. They still rotate at maybe 5,000 or 7,000 rotations per minute. And, well, you might ask, why can't you make them go faster? Well, actually, the centrifugal force on the disks would be so high that they just shatter. And since you can't have that, well, the speed has pretty much stayed the same. And the read heads also really physically need to move around on the disk. So therefore, there's not that much that you can squeeze out in terms of speed here. I mean, it's just physical limits. More interestingly, solid-state drives, well, you get about, right now, 500 megabytes a second easily. You get at least 10 times the random request rate that you get for a hard drive. On some fancier ones, it gets a bit better. But that's a bit what you have in terms of computers. Important lesson out of this for you here, if you ever implement something, try as much as you can to run your instructions such that you access data in bulk, as in sequence rather than random reads. This is one of the reasons why usually sparse matrix linear algebra is easily a factor of 10 slower than dense matrix linear algebra. Okay. Network interface, well, essentially gigabit networks are sort of standard. Much faster ones are really expensive. But what that really means is that if I want to copy the RAM across the network of a standard machine, it can take me between 1 and 10 minutes. That's a substantial number. Basically, the network interface hasn't really sped up much over the past 4 or 5 years. The memory has gone up quite a bit. So now transmitting the main memory to another machine just takes 4 or 5 times longer. Copying a terabyte of data across the network takes a day. This basically means operations that run on a terabyte per machine, you can pretty much forget about them. You want to have things that, where each machine has maybe tens of gigabytes, maybe 100 gigabytes. If you operate on a terabyte per machine, you're doing something wrong. Power consumption is pretty much constant. I mean, it's between 200 and 400 watts, depending on what you use. GPUs actually use a massive amount of power. This is one of the main reasons why they are not quite as popular in the server centers as you would expect. The other thing is, well, unlike your high-end supercomputing center at the university where you have, usually custom hardware, and it's all very much non-standard, this stuff is built to scale. And building to scale means you buy cheap in bulk. It doesn't mean that we necessarily buy terribly high-end hardware. We buy cheap hardware. Because if we get twice as much cheap hardware, and occasionally some machines fail, well, you could say, oh my God, that's the end of the world. Or you could just say, well, let's design algorithms that are actually designed, that are capable of dealing with this, that are fault tolerant. And in a way, you're pushing the onus onto the developer, onto the engineer who designs the algorithm, to make sure that you still get something useful out of it, even if some machines fail. This is something that I haven't really seen very much people thinking of in the machine learning community. Design your algorithm such that if one of your machines fails and needs to recover, the algorithm will still work. So there are some approaches that you can port over. For instance, robustness maps fairly nicely over to that. But a systematic analysis of this would be quite fun. The other thing is, of course, you design the system to grow. So, you know, you add more servers. And they quite often keep on just running. So, server centers. You know, 10,000 servers is not unusual. You aggregate them into racks. So basically, that means you have maybe 50 to 100 machines on the same switch. And within the same switch, you have essentially perfect point-to-point bandwidth. Between the racks, you have reduced bandwidth. So if I can, it's good if my algorithm can exploit the fact that I'm on the same rack, but it doesn't degrade too much if I'm on a different rack. So, you know, if I, for instance, have a scheduler, it'll be good if I can exploit this. Then, you know, machines die. The OS might crash. The disk might die. The entire computer might blow up. The entire network switch might die, in which case you lose, well, 50 machines at once, or maybe it just gets flaky and then it comes back. And yeah, I mean, basically anything that you can imagine can go wrong. I mean, you know, you have 10,000 machines. Well, think of it this way. If 10,000 machines were to stay up for a day, that's the same thing as having a single machine keep on running for 20 years. Sorry, 30 years. So that roughly gives you an idea of how unlikely this is. The other thing is you have server centers worldwide. So the applications need to run between different server centers. You need to do load balancing, data transfer, all that. So this is just to get you thinking a little bit about when you design algorithms that they better be capable of dealing with this in some way. Okay. To give you a bit of an idea, I mean, I'll just put the numbers up there. You can read them up later. But obviously, I can't tell you what we pay for our servers. But to get some idea of how much things cost, you can, for instance, go to Amazon, look for the EC2 prices, or the S3, so basically for storage and data transfer and machine time. And that gives you some idea of how much a machine costs per hour. $1 an hour is not an unreasonable number, depending on what you use. So for instance, if you have like this quadruple extra large with GPU, okay, well, you pay $2, right? Or high memory double extra large, okay, you pay $1 for it. But that gives you some idea of how much things cost. Storage, I think they're making quite a killing on that. I mean, they charge you like 10 cents a gigabyte per month. Data transfer is really the killer. And that's because actually network bandwidth hasn't really scaled up quite as rapidly as CPU and disks. So if you have an algorithm that needs to go out and essentially crawl the entire internet, well, you're going to pay probably more for getting the data into your server center rather than anything else you're going to do with the data later on. So good scheduling algorithms and so on for that are really useful. Okay. Processing in the cloud. So to give you a bit more ideas of the amount of data that we get. So suppose we have billions of web pages. We might have billions of queries in the click and query log, and then maybe millions of data ranked by editors. And I'll get to this, that this was actually a really dumb thing to do. We're not in search anymore, really, as in the core search is outsourced to Bing, so I can talk about that. Now, storing the data is actually fairly cheap. Suppose, 100 billion web pages is a reasonably good number for, what is actually interesting. I mean, yeah, there are a lot more, and so we had caches of, cache tiers of different quality. One of the better ones was called WOW, which sounds great until you know that it's called worst of web. But 100 billion web pages lets you do a lot. Suppose I store 10 kilobytes per web page, which isn't very much. That would be basically just the text. We're talking about a petabyte. If I want to store this on Amazon S3 for a month, it's not too bad, right? It's $10,000. Now, processing the data, suppose we process only every 10th of those web pages, and suppose we only spend 10 milliseconds per page, which is really nothing. And then if I maybe, that means like 10 days on 1,000 computers, and that's around $100,000. Now, 10 days is actually a long time, because during that time, a lot of web pages will have changed. So once you're done by the end of those 10 days, you need to crawl the page again and do things again. On top of that, 10 days is not really acceptable for any page that might have changed already within a day. So you need to figure out which pages change rapidly, and you update your cache optimistically. And it's useful if you have some mechanism to alert you that a page has changed. Google Analytics, for instance, does that, and I guess this is one of the reasons why they have it, plus a few others. Now, getting the data, that's the real killer. So to put things a little bit into proportion, suppose we have like a 10 gigabits per second link, then it would take about 100 days to gather the data, right? Now, 10 gigabit, well, you know, that's not so much, right? That's like 10 Ethernet cables. Well, actually, if you think about the Asia-Pacific China 2 cable, which at least last year the state of the art was 2.5 terabits per second bandwidth, you know, 10 gigabits is actually a fair chunk of that bandwidth, right? So you probably wouldn't get like 1/10 of the entire bandwidth between the United States and China, right? I mean, that would cost you a lot of money. And correspondingly, if you look at the EC2 price, well, you know, you could probably look into spending about $1 million just on getting the data. So that gives you a little bit of, you know, relation between getting the data, processing it, and storing it. Storing it is the cheapest. Getting is the hardest. So now, but let's just start with the storing part. How would you store things? So this was like a really ingenious idea by Sanjay Gemawat, Gobioff, and Leung in 2003, the Google file system. And the Hadoop file system works essentially the same way, but okay, they had it first, and the Hadoop file system is essentially a clone of that, give and take. I mean, there are some more differences, but okay, so what they realized is, okay, well, storing data is cheap, so why not take a large number of essentially Linux servers, stuff a lot of disks into them, and use them to store data, okay? So for good measure, to make sure that if a machine dies, you don't lose data, you replicate it. But you replicate it actually 3 times. 3 times because, well, not only do you care about keeping your data, but you also want to make sure that if one of your servers dies, that you still get decent bandwidth, right? And in some cases, if a file is really popular, you might actually replicate it more than 3 times. Now, the ingenious idea was to say, well, look, we're storing really large files, so let's break them up into chunks. And in this case, the chunks are like 64 megabytes. And then I basically have replication at this chunk level. So each of those, well, cheap servers just has a lot of files of size 64 megabytes. You standardize it by that, so that makes the access really simple. And then you have a metadata server sitting on top, which does nothing else, but if you, say, want to have such and such a file, it looks up, okay, who has the data, and it just dispatches the request onto the servers. And then the corollary out of that is actually writing data is really cheap, because you write into one server, and that server automatically goes on and replicates to all its friends. So that gives you good write-through. If I want to read, I get the aggregate bandwidth for the read performance, because I can basically just more or less in parallel start reading different chunks if I want to. If I have several machines accessing the same file, well, you know, they just talk to different servers, so this is all reasonably well handled. And of course, it's fault tolerant, because what happens is if you lose a machine, okay, you lose all of those chunks, but then the metadata server starts issuing replication requests to make sure that the other 2 copies are just copied again.
So do you always ping to find out the health of the machine?
Okay, this is a very good question. So there are a number of services that allow you to ascertain whether machines are alive. A heartbeat is one of the mechanisms how you can do this. So basically that means you have a little process running on each machine, and it's set up to basically send the information, I'm still alive, back to the main server. And you can do that, and that's a fairly effective mechanism. There are more sophisticated mechanisms that then use interesting distributed protocols. So Zookeeper is, for instance, an open source version, as in this is the Yahoo version that's been open sourced into Hadoop, which allows you to do more interesting things. Essentially, it behaves as if you had a shared file system into which you can write things. But it doesn't actually store things on file, but it's basically just synchronized with a synchronization protocol called Paxos between different machines. And yeah, so you can just try that out. It's actually a fairly nice system. To go into a bit more details, I've already mentioned some of them here. So you have a name node, which is basically like your directory server. That one itself is replicated, and there are lots of details to get right in order to make sure that if the name node dies, your system comes back up quickly. I mean, one thing you can obviously do is you make sure that the name node is of very high quality, fairly reliable hardware, but still it might die. And so what you have is basically you have a whole bunch of other name nodes copying the master name node, and they are on standby, and as soon as the main name node dies, they just jump in and fill in that hole. For a write, you just ask the chunk server, okay, well, which node should I write to? And then you just talk to that node. You don't want to go to the main node. Let's just compare things a little bit. What you get. So the Hadoop file system or the Google file system, what you get, and that's really good, is you can get really fast block writes and reads. This basically runs at disk speed. It's very fault tolerant. And the good thing is you can add machines or retire them, and the thing just keeps on running. So you could just have, a mechanism by which you replace a few machines on a daily basis, and so you can just recycle your hardware, adding more capabilities, and the file storage will just stay up. And from the application's point of view, you won't notice anything. However, the way it's set up, because you write entire 64 megabyte blocks at once, it's really absolutely atrociously awful for random rewrites within a file. Because if I even just write a single byte in a file in a random location, that single byte gets amplified into a 64 megabytes write. And it's not really a file system, so the usual. I mean, it behaves as if it were one, but it's really specialized for a certain type of operations. It's really great if I want to dump a lot of data quickly to disk, or if I want to stream a lot of data from disk into another process. For those things, it's perfect. For random reads and random writes, it's fairly awful. I'm not sure in the Google file system paper, I think they write that they don't even support random writes. And that's for a good reason. NFS, it's not really a distributed file management system. I mean, basically, you just gang a lot of machines together. People also say something like no file security, but whatever. Lustre looks really good on the surface. It's a proper file system. It's really high bandwidth, so you can have fast interconnects, and you actually exploit them. The problem is it isn't very redundant, actually. So the redundancy comes from just making each of the server nodes really redundant by having the RAID 5, for instance. But if an entire cabinet dies, well, you have a problem. And it's really hard to add more storage easily in this case. So Lustre may be good for some applications where you need cheap disposable scratch space, and where if some machine dies, well, okay, you lose the entire cabinet, but sometimes this may be an acceptable trade-off. So a lot of engineering is looking at trade-offs. And for high-performance computing, that may be good enough. If this happens once a year, then, okay, sure, your simulation is a bit slower. On the other hand, if you need to have a service that's up 24/7, then if Yahoo Mail goes down once a year, well, we get a lot of angry users. So it's really looking at good trade-offs. MapReduce. So the main scenario is you have a lot of data and a lot more than what you can process with a single machine. You store it in a distributed fashion, and then you move the computation to the data. Okay, let me repeat. You move the computation to the data, not the data to the computation. I'm repeating this because I've seen a lot of, and it's not meant in a terribly bad way, but, sorry, yes?
Just a question still returning a bit back. Looking at those file systems, do you not care about, let's say, bitrate when you have such huge amounts of data, or is it just not important because you're dealing with text and you don't care if you get bits wrong here and there?
Okay, so bitrate. Okay, so I was glossing over those details. Basically, bitrate might be that some bits on your disk go bad. Well, there's a very simple way how you can deal with that. You don't only store the 64 megabytes block of data, but you also store a checksum for it, right?
Yeah.
And so like an MD5 hash. So the chunk server reads that 64 megabytes block, it computes the checksum, and if the checksum is wrong, it goes back screaming to the head node and says, by the way, my block is wrong, tell this guy to get it from somewhere else. And that way you can deal with bitrate. Because yes, we care about our bits being accurate. Yes. So thanks, very good question.
What's the method for dealing with head failure?
With what?
There's this head node.
Yes.
What happens when if that
Yeah. Okay, so what happens is basically you have usually a couple of additional head nodes which listen in on all the traffic that the main head node gets. Or the main head node might send digests every second or so to them. So there are various technical solutions, and I would very much suggest that you refer to the papers on the Google file system or the technical description of the Hadoop file system, how exactly it's handled. But the general spirit is you have a couple of copies of those, and, well, you then, basically when the head node dies, they just fail over. The GFS2 system seems to have a more ingenious construction which doesn't actually require a single head node anymore. And that would, yeah. Well, not all of that is actually publicly released. And so you'd probably have to best ask somebody from the Google Systems team about how they do it. If somebody from Google is here willing to tell us about it, I'd be more than happy to hear about it. OK. That said, the head nodes die very, very rarely. And if so, then the failover is there quickly. But by the way, thanks for asking those questions. I'm delighted that I'm getting them. So MapReduce. So the idea is you have tons of data, can't really process it in a single machine. So, well, we store the data in a distributed fashion, and you move the computation of the data. I've seen more than one research proposal to the ARC or the NSF, and actually some of them that got funded, where people talked about a web-enabled machine learning system. And the idea is that they provide a computational server which does all the data analysis, and you send the data there. OK, there's pretty much everything wrong about that. Because you're sending it over the internet, right? Low bandwidth. Computation is probably not going to be the killer unless your algorithm is really slow, and it won't scale. So yeah, don't. So map. Map does the following thing. It applies a function f to the data as distributed over the mappers. And the important thing of that is that this function f, and in combination with the reducer, is such that regardless of the number of mappers that I have, I will get the same result out of it after I've run the reducer. And that doesn't necessarily apply to all possible functions. But for instance, if I take averages or take mins and minima and maxima, I can do this. For averages, I need to keep the counts, of course. And I'll show you an example of that in the next slide. Reduce then takes all the data that the mapper emits, and it combines it, and that's hopefully a result. Fault tolerance is actually quite easy in this case, because all you need to do is you just need to remember, well, which data would have gone into which mapper. And after all, these are going to be those 64 megabyte chunks from disk that you more or less dump into the mapper. And so if a mapper dies, you just fire up another machine and send the data there. If a reducer dies, ditto. All you need to assume is that you would have logged the data emitted from the mapper somewhere on file before you send it to the reducer. So this is really a bipartite graph. And we'll get to that bipartite graph metaphor in a moment. So let's look at a very simple example, item count. So let's say I want to do word counts. And so what you do is basically each mapper gets like some unsorted chunk of data. Right? Like, for instance, here we have the hexagons and squares and triangles. And each mapper gets like some of that data. And each of them then goes and counts how many times each of those things occurs. And then they emit into the reducer these counts, like 1, 1, 2. Well, basically, they would emit the counts. Yeah, OK. Well, if you just want to count triangles, it would be then 3, 2, and 1, whatever. These things go into the reducer. The reducer takes all those vectors and sums them up. If I have several reducers, I might have one reducer which takes care of the squares, another one taking care of the triangles, and a third one of the hexagons. So that way, even if the mappers emit a lot of data, it's quite easy still later on. And this gives me more or less perfect parallelism. The only thing I need to do is at some point write to disk. That writing to disk is actually quite nasty in some cases, and I'll show you a way how to get around this. OK, good. Is everybody comfortable with the item count in MapReduce? Because it's like the simplest example that you usually would do. OK, good. Let's do something that's a bit closer to machine learning, k-means. So how would we do k-means in MapReduce? And again, it's really, really easy. You initialize some random cluster centers. Okay. Now you send to the mapper those random cluster centers and chunks of data. Each mapper then assigns each point to one of those random cluster centers, like these guys here. And then it sends further on to the reducer. Basically, reducer 1 gets cluster 1, reducer 2 gets data from cluster 2, reducer 3 gets data from cluster 3, possibly only some summary statistics of it, depending on how you define your cluster. The reducer then, for each cluster, aggregates all the data, comes up with a new cluster center. That can be as simple as just taking the average. This is then sent back for the next iteration of MapReduce, again to the mappers. They, again, assign the data to the cluster centers. They send it on to the reducers. They update their cluster centers, and you keep on going. Yes?
So in the map phase, are you sending all of your cluster centers to all of the mappers?
Correct. So you've picked on a really, really important point here. So let me repeat it. We are sending all the cluster centers to all the mappers. So can anybody see a problem with this? Fun? Well, you need to send it, yeah. I can do that maybe with multicast, so it's not quite so bad, but can somebody see a much more serious problem with that? It's sequential, yes, okay, sure, I need to send it through in sequence. But the much bigger problem is the following. Well, think about what you want to achieve with clustering, right? One goal is you want to be able to have, you know, a more sophisticated model of the data as you get more data, right? So the number of cluster centers should actually increase as I get more data. Okay. So what happens? At some point, the list of cluster centers actually is fairly large. It's too large to be sometimes handling a single machine. Furthermore, actually, for each of the comparisons, things get even slower. So the algorithm doesn't scale terribly well. So yes, there are lots of papers on, by the way, here is how we do clustering on MapReduce. And then they try it out on data sets where the number of clusters is sufficiently small that you don't notice all the pitfalls of the algorithm. Yeah, so this k-means is something you may want to do but probably shouldn't. Yes?
When you're updating the cluster centers, how do you do it without knowing the data? I mean, aren't you moving the data around?
No, in this case, I'm moving aggregate statistics around. So for instance, each mapper computes, you know, number of points per cluster and the average for that cluster. Now, that is already a significant data reduction. Now, each reducer gets all the counts from each of the mappers for a particular cluster ID and all their averages. And that scales fairly well. But the big issue is really that each mapper needs to hold all the data about the cluster centers. So the problem arises that if I have too many cluster centers, I run out of memory. So even just the data representation for the model may be quite sizable. And obviously, you can only do a limited number of iterations this way, because each time you run MapReduce, well, you actually need to request, by the way, I would like to have those machines. There are ways around it by, you know, talking directly to the scheduler, and for instance, the next version of Hadoop will have the yarn scheduler available, which lets you talk directly to the scheduler as opposed to going through MapReduce. But yeah, there are a couple of reasons why this is more of a toy example. Okay. Now, there are some guys in Microsoft who actually looked at this bipartite graph problem and came up with a really elegant improvement of it. So this is Dryad. And essentially what they realized is the following. Well, look, the data flow that we are modeling here is a bipartite graph. Why not generalize it to an arbitrary directed acyclic graph? Okay. That's ingenious observation number one. Ingenious observation number two is to say, well, writing the data to disk between each of those nodes is madness, because quite often each of the individual processing stages don't do something very complicated, so why not just, you know, gang some filters together in memory? That's what they did. So what they did is they allowed for 3 different interfaces, namely a memory FIFO, or going through the network, or going through disk. And that allows you to have a much more modular composition of the entire computation graph and have data flowing through. So when I read the paper, I thought, wow, this is really awesome. Then I talked to Michael Izard and said, well, look, you designed something really great. So do people really use all those other interfaces? Because I thought, you know, this is really cool. And then he said, no, actually, they all write to disk. I don't know whether they still do that, but that was like a year and a half ago. I was a bit sad when I heard this. Here's something that Yahoo recently released, S4. And it's, yeah, probably the most scalable version of all of this, and also the easiest to implement. It's open source. You can download and play with it. It requires a little bit of techniques that I'm going to discuss a few slides further down the line. It's basically an online data flow setting for that. So you have a directed acyclic graph, like this. You could actually have cycles in it if you really wanted to. And each of those things is processed by some processing element. Now, the processing node does the following thing. It basically receives data with an instruction, by the way, now you should act as processing element number 2. So basically, maybe take averages. Takes the data, does something useful with it, and dispatches it. And it looks at, well, by the way, I acted as processing element number 2. Well, now I should send it to number 5. Then it looks at the key and where it needs to be sent to and picks some random other machine in the pool, and that some random other machine I'll discuss in a moment, to parallelize this as well. So what it does, therefore, is you can essentially scale data flow perfectly among a lot of machines. The only caveat is that each machine needs to be capable of doing any of the jobs, and you might run into some issues with memory. But this is, for instance, what's in production for sponsored search data serving. So that's actually where the name comes from, sponsored search streaming something. And I recommend you to read this paper by Leo Neumeier and co-workers. It's a very nice paper. And yeah, this distributed hash part I'll talk about in a moment. But this is the key difference between Dryad and this, is that this is all online data flow programming, whereas here we have the classical, well, send a chunk from here to there and go further. And the other difference is, for this you need to essentially install some Microsoft tools. For this you need to install some other tools. Yeah. But basically, this you can use commercially. For the other one, you can use it only under a Microsoft academic license. Yes?
Can you give an example of the processing element? Is it just a function?
OK, so one thing, for instance, would be a running average. Another one would be to have an online algorithm sitting in the nodes, right? And you do stochastic gradient descent. You then probably want to do interesting things, how to aggregate your parameters and to coordinate them. And, well, this goes a little bit beyond the overall streaming architecture, so you need to establish a few more side channels. But for instance, you could do parallel online learning by exploiting an architecture like this. For instance, one case where you might want to have something like this is if you want to serve ads to a lot of users. Then you use a suitable hashing function to make sure that a particular user always arrives at a certain machine, unless the machine dies, in which case it just gets rerouted. That way, I know which ads you clicked on just in the past minute, and so I can use this to, target other ads to you. Or for instance, I can avoid showing you the same ad twice. And I can do this in a perfectly scalable fashion. Okay. So that now concludes pretty much the, systems part. Sorry, one more question.
Don't you need to move data in this?
Do I know that?
Don't you need to move data again in this framework?
Absolutely. The data flows here through the graph.
But this is bad, right? From the 100%.
Well, I mean, you need to process it anyway. And at least now this is for an online setting. So the data needs to stream in somewhere from the network anyway. Of course, I could screw up insofar as one of those nodes would emit a vast amount of data, in which case I completely swamped the entire network. But in the absence of that, yeah, I mean, I'll actually need to move data around anyway. So yes, you're right. It requires quite some use of data flow, but also the other processing paradigms that I've showed you at some point need to move data around. You want to make sure that you squeeze as much as possible within a single machine, which is exactly why you have this memory FIFO, which is really a very, very simple and very ingenious construction to make sure that I can agglomerate several filters within a single machine. But yes, at some point you'll need to cross the boundary to a different machine. This sometimes may also be necessary for load balancing purposes, because you don't quite know which user is going to be a heavy user or not. If I have a static assignment just of all the jobs by users, then some machines might actually get loaded a lot. So the tail behavior might be quite bad. To give you a quick idea of what happens. So this is quite a useful property of random variables. Does everybody know how the maximum of a set of random variables behaves? Okay, let me quickly give you the derivation. Source select. Document camera. Okay. Suppose we have some random variables xi.
You have to click send to screen.
Oh, okay. Send to screen. So, okay, so suppose I have some random variables xi, where I is maybe going from 1 to n. And what I want is, okay, good. What I want is I want to have some variable y, which is defined as the max over all these random variables xi. Now, this basically, so now what I can ask is I can look at the cumulative distribution function of y and look at the cumulative distribution function of x. So fx, just to remember, of x is the integral going from minus infinity up to x of px of chi d chi. And this is nothing else than the probability that, with respect to x, that chi is less equal than x. Right? That's the cumulative distribution function. Ditto for fy. That now maybe some variable nu is less equal than y. Okay. Now, what I therefore need is that if y is the maximum over all of those guys, right, I need to make sure that all of these probabilities hold. So this is given by the product, and if I draw them all independently, I going from 1 to n fx of y. Okay. So one idea to see what happens is, suppose this is the cumulative distribution function for a uniform distribution. Let's say here is 0, here's 1, here's 1, 0, this is f of x. Then for a uniform distribution over the unit interval, we will get a straight line. Now, if I have n random variables, then I take this line and I raise it to the power n. And what happens is something that behaves like so. Right? So in other words, up to some very large number here, there's essentially no probability that, so this would be fy, this is fx. Basically, there's up to this value here, essentially, with very high probability, I don't have anything that's smaller than that. Well, what this means is that if you take the maximum over a bunch of random variables, you very, very quickly end up in the tail of the distribution. Okay. Now, if I have a bunch of users, each of those users has some access characteristics, maybe the amount of data that they give me. And my overall system performance depends on the worst behavior, basically on the worst user, then very quickly end up in this region. So you need to be very careful about this when designing your algorithms. So there's an interesting paper at WWW 2011 by Sergei Vasilevsky. And it's called something like the curse of the last reducer. And basically what it says is, you have a MapReduce job, and almost all of your reducers are already done, and then you're waiting for the last reducer. And you keep on waiting and waiting and waiting and waiting. And then he discusses a couple of ways how to, well, address this. Okay. So this is actually something that as soon as you build large systems with many machines in it, will start hurting you very quickly. It's very simple statistics, but the effect of it, unfortunately, is quite nasty. You can actually also use this to your benefit in a randomized algorithm. In a randomized algorithm, if I have a large set of random variables, and I want to pick something that is, with high probability, very large, I only need to pick a small subset of them. So there's something that I would call the 59-95 rule. And basically it goes as follows. If I draw 59 instances independently from a set of random variables, ID, that are ID random variables, then with 95% probability, the maximum of those 59 random variables is going to be larger than 95% of all the other random variables. Okay. So as your homework assignment, derive this. Okay. And this is basically already giving you almost the answer, right? Because these are also the quantiles. So in terms of quantiles, I get exactly a uniform distribution between 0 and 1. And so now you just need to work out exactly where the 95% interval here is, right? And you cut there. And you just take logs so you get the number. So derive that as your homework. Good. Any questions before I move on to data flow? Pardon?
We have a lunch break.
Oh, we have a lunch break. Okay. I was actually assuming that I'd get through this and a few other things quickly. So, okay, I definitely won't be getting through all my slides. Okay. We're at slide number 20 of 310 slides right now. Okay. Good, then there's lunch break.